little bit about displays. We have been, as I mentioned in the last video, using the EVIC display. This is a little piece of hardware and software done by Andromeda Interfaces in San Diego, California. And it uses Windows CE, and it's kind of a secret. They let us do some things, but not very many. And you have to do it in Visual Studio 8, not anything later. And Windows, of course. This particular skin they did for the Orion BMS, and we normally change it to use with our Tesla drive unit. But I got some with the Orion BMS skin to use with batteries, and it was quite simple to suss out the CAN messages that it uses, and it's displaying our voltage, our current, and our temperature, our high cell and our low. It has a little battery from 1939 that is green, and then it goes down and gets red. And it's a nice display. I like it. There's not much you can do with it, but it's the problem has been that every time we've ordered them, because we have found a use for them, they've increased the price. And I tried to order some in July, and they told me the earliest they could get them in September. They got on their website, I think they're actually going to deprecate it. It's they have a new display that is smaller and even more stupid, so I don't want to play anymore. Of course, we have our laptop, and one of the ways that you monitor your operation of the controller is through a USB port connection to a laptop with a standard terminal program, just ASCII text. And this works okay, but we had an interesting customer, Congressman Thomas Massey from Kentucky, and he's an MIT EE type guy, but he's in the U.S. Congress right now. But he has built his own home on his farm literally by hand, native stone out of the ground on his farm, piled up to be a house, a really nice one and a big one, timbers locally, and of course he has entirely off-grid for everything, water and electricity and so forth. He bought a Tesla battery pack, and he and his sons took it apart and made 16 modules in a 48-volt system, and bought our controller and live with this every day. I mean, it's not a hobby with him. That's how they get their electricity. But he wanted his own display, and so he made one on a Raspberry Pi that works by capturing my serial stream out of the USB port. And I was quite taken with his display. I hadn't looked at a Raspberry Pi in a number of years, but found it a curious choice. And using serial port data, also kind of curious. But he did a nice job of it, and it was a great looking display. So I sucked up a little bit, and he gave me the source code. And Colin and I have been looking at it and have come up with some improvements, I think. And this is the Raspberry Pi 3 B+. It's their latest thing. It's in with a 7-inch touchscreen, again by Raspberry Pi, and in an enclosure. I don't know who does the enclosure, but Colin found it, and we've got them and put it in there, and it makes a great little lightweight display, and it's non-trivial. This is a 1.4 gigahertz quad-core 64-bit processor. It uses micro SD cards for data storage. I've got a 32 gigabyte card in there, which costs $10. And it's a whole Linux computer with a desktop and Raspbian, kind of a variation of Debian distribution of the Linux. Distributions like the Linux kernel and a set of selected open source software programs and tools. And it could be anything. But if you do a selection, a set of these, it's kind of your own distro or distribution of the Linux kernel and tools. And Raspberry Pi has been doing this for actually a number of years. Again, a British group aimed at education, teaching kids computers and Linux programming on a very inexpensive single board computer. But it's gotten to be, this one's got 4 USB ports, an HDMI port, an Ethernet port, and it does Wi-Fi at both 2.4 and 5 gigahertz and Bluetooth. It's actually an amazing little computer. And they've done a 7-inch touchscreen that actually goes with it very well. Has 1 ribbon cable and 2 power wires, and the Raspberry Pi screws right down onto it, and then you put it in this enclosure, and it's really quite the thing. So Colin and I have been looking at that, and we got some CAN boards that sit on top of it to do CAN just like we do the EVIC. And in fact, we use the same EVIC CAN message IDs and messages. But I got to looking at it, and in order to do anything with it, you have to connect to a network, and you normally do that wireless to your home access point, your router, wireless router. And so I got to looking at it, and I've had a theory for some time that CAN and UDP, User Datagram Protocol, are kind of similar. They're not identical, obviously, but they're connectionless. There's no error checking. There's no retransmission. And UDP has a function where you can send it to the broadcast address. And it's kind of like CAN. You're just broadcasting messages, hoping that anyone that might care can then receive them. And so I got to playing around with UDP CAN, and we've kind of gone that way, and it's really quite interesting. We can take this device and put it in the kitchen. It doesn't have to be here. It has a little USB connector, but that's to a wall wart power adapter for 5 volts. And so this can get data from our Powersafe 100, and it displays it. We kind of copied Thomas's little thing with the Tesla dial and some little screens. This is a log screen for power. Then here's a cell display. And so we kind of took his interface and jazzed it up a little bit with some more features and with this UDP CAN. And, well, we did most of it a little differently, but it was Thomas Massey's original concept. And we've kind of advanced the token on that, and I'm very pleased at this point with the outcome. In a few short weeks, we have a much better, more informative display, and even the screen. This one is kind of glary and simple. This has very good contrast, as you should be able to see on the camera, and it's just a nicer looking display. A little 800 by 480, about the same as the EVIC, but it's brighter and clearer and with better contrast and blacks. And so that's the direction we're going to go. Let's take a look. I'll do a walkthrough with you on just what this does with the Powersafe 100 and how it does it. Let's have a look. We're going to talk a little bit today about our new display device. As I've mentioned in a past video, we're having difficulties procuring the Andromeda Interfaces EVIC display that we've used for 4 or 5 years to display CAN data type interfaces. Andromeda Interfaces is a very small company in San Diego. I think they're deprecating the use of this device entirely. The EVIC is slow. It's a Windows CE application. You have to program it using Visual Studio 8.0 and not a later version, and an earlier version of Windows. And it's just a mess to maintain and program, and it's a kind of a slow, ugly device. But the big problem is every time we reorder, they raise the price because we use it and have found application for it, and they know that. And so we've kind of been held hostage by a not very professional supplier. And so we need a new display device. We're up to charging like $800 for this display. So there's no question it's not very popular because it's too expensive. And so we go. This is our screen. What we've done is gone to a Raspberry Pi type device with a 7-inch touchscreen. And both are the official products of the Raspberry Pi organization, a British group that wanted to bring Linux computing to the masses, and students particularly. And they built a small Arduino-like board that runs Linux and the Debian distribution, which they've kind of revised for their own purposes and released as Raspbian. But it is a Debian variant of Linux running on a small computer board. This has gone on for a number of years in fits and starts, but it's been enormously popular, and there's several million sales of these devices now. And so the price of it's extremely reasonable. The bare necessities of what we're doing with a board, a 7-inch touchscreen, an enclosure, and so forth, a power supply. About $180 our cost on that device. The best part is that it puts us back in Linux and GCC or G++, the GNU ordinary language compilers. And we use the GNOME graphics library, GTK. We can make fairly attractive GUI type programs and quickly compile them using ordinary free compiler tools. The latest version of Raspberry Pi actually is the 3B Plus, and I find it a remarkable computer. I gave up Linux for Lent in the Lenten period of probably 2006 or 7, and went to Mac OS X. I used to build my own tower computers at a cost of $10,000 or $12,000 a piece. And this little board 12 years later is probably more powerful than what I was building in 2006. It has a Broadcom processor that's an ARM 53 processor with 4 cores,
and operating at 1.4 megahertz. It has a gigabyte of RAM. Your operating system is held on what then becomes the system drive, which in this case is a 32 gigabyte micro SD card. And so this is all tiny with more RAM and more drive space than I had in 2006 for a remarkably low cost. Additionally, this little board has an HDMI output, general purpose input and output, somewhat like an Arduino, 4 USB ports, both 2.4 gigahertz and 5 gigahertz Wi-Fi, and Bluetooth BLE, all built in to the device. And this opens up some remarkable opportunities for us. As you know, displays are not our main line of business. We're doing controllers for Tesla batteries, and we use our little EVTV CAN DUI, which is like an Arduino DUI board with CAN ports on it. Our next generation of that, which we've also been working on, is the EVTV ESP32 CAN DUI, and that uses the Espressif ESP32 chip, which has Wi-Fi and Bluetooth built in. What we've been working on recently is the concept of doing CAN wirelessly. And what we're experimenting with today is UDP packets. Universal Datagram Protocol is a much more basic IP protocol than TCP, Transmission Control Protocol. TCP, you establish a connection between one machine and the other. UDP is just kind of raw packets. You get to define what's in them and how big they are, and you simply send them out. And we've done videos of how to get an NTP network time protocol time mark using UDP datagrams. What we're experimenting with now is the transmission of CAN packets, which are used in automotive over a 2-wire system, using UDP on the broadcast address of an access point, an AP. The access address is whatever your IP address is, with the final number being .255. And UDP packets transmitted on .255 can be received by any IP, any device with access to that access point. It's a broadcast address. And UDP inherently is connectionless. You don't set up a connection between two devices. It's simply a raw packet transmission. And so we can broadcast that on the broadcast address. And of course, you have to define a port. Various services, FTP and HTML and Telenet and so forth, each have ports that at that IP address they use. In this case, we can simply make up a port, and we've made up port 6500, primarily because you have to have root access to monitor ports below 1024, which is where most of the popular ones are. We don't care about popularity or even universal applicability, as long as we agree on a specific port on both ends of the transmission. We can do that. And so we can set up our Raspberry Pi to get on the access point, get an IP number, and then monitor port 6500. And in our ESP32 device, which we use to now control the Tesla battery modules, we send out CAN data on the CAN port for our EVIC display, and to do other things, control chargers and so forth. I can simply add a little routine to every CAN packet that I send out of the CAN port to also send it on port 6500 to the broadcast address on a Wi-Fi on the access point. And so, because I have a connection to the access point with the ESP32, which does have wireless capability, I can simply blast my CAN packets that I'm sending out the CAN port anyway, as a wireless UDP, user datagram protocol packet on port 6500 and the broadcast address .255. And any device on that access point, if it was monitoring port 6500, would in fact receive those packets. Now, it has to be looking for them for it to matter, but it would receive them. And so we take our Linux Raspberry Pi and connect that to the access port to listen on port 6500, and we can actually get CAN packets across the wireless connection and receive it in the display. Now this opens up some marvelous new capabilities. For example, our Raspberry Pi needs 5 volts and a little wall wart that you plug into the kitchen counter and plug into the Pi will give it the 5 volts, and it will come up and run this program and monitor that port for UDP packets. So we're not tied to the battery or to the battery controller at all. In fact, we don't need line of sight to that device. We just need a connection to the access point in your house. And, of course, the battery controller needs that as well. And so you can have your Tesla battery module and controller and inverter out in the garage or down in the basement or in a separate building, as long as it has connectivity to your home access point, and have this display device in the kitchen, and it will receive those packets and display information about your Tesla battery. And so this is kind of the thing. This is the screen, that the basic presentation of our device. And I'm going to go turn on UDP transmissions from my ESP32, and I have this in kind of a test mode. So this isn't real data. In fact, it's test data that varies specifically to test my software here on the Raspberry Pi. And the screen, I'm using VNC a program to control devices remotely to observe that screen, that 7-inch touchscreen on my Macintosh, Mac OS. And so here we see the basic presentation of the display, which is quite different from the EVIC display. And we're going to go through some of the data that we're receiving here and what it means. But understand this would be somewhat more steady if I wasn't actually running up and down the current, the voltage, and the individual cell voltages for experimental purposes to troubleshoot the software. But this is our main display. Let's start up here. You see a display of amperes. This is the amount of current that the battery is putting out or taking in. In this place, we're putting it out. It's a positive value, and that is discharged from the battery. And that's at 221 amps or whatever. Over here, we have the voltage, which I'm also varying, of the pack. And that is the entire pack. On Powersafe 100, we have 2 Tesla modules in series for nominally 44 volts. And then we have 10 of those sets in parallel for a fairly enormous, about a 75 or 80 kilowatt battery pack capacity. And so on the right side of the dial, we're displaying our kilowatt output from the battery pack, and ostensibly the inverter. And we have that number displayed here. Right now we're discharging at 16.40 kilowatts, 1,000 watts. And that's displayed up here. And we have a logarithmic display, very reminiscent of Tesla's kilowatt output on the Tesla Model S instrument cluster, showing our discharge of the battery in kilowatts. And as you can see, that's coming down. And that's displayed in red when it's discharging. And as our amps comes down, that we're receiving the UDP data from the controller, we can see the resulting kilowatts, amps times voltage, is power in watts, and that is decreasing as our current goes down, even though our voltage is going up right now. And so it is slowly coming down, and it's going to hit 0 here. And now our current is going to go negative, and we're actually charging. And this is power into the battery, and I'm very pleased to report that we're doing some fabulous hours-long, afternoon-long charges of the Powersafe 100 from our AC-coupled Solar Edge grid-tied inverters. This is working extremely well. And so here's our dial showing a green or charging scenario here. And we're, as you can see here, at 8.88 kilowatts of power. And so that is current and our voltage. This is actually the temperature of our highest value of all of our. We have 2 temperature thermistors on each Tesla battery module. We can monitor up to 62 battery modules, and this will display the highest temperature that we receive. And this, of course, is our voltage for the pack. And again, here we're charging at 390 amps here and 11 kilowatts. We're routinely seeing 200 to 225 amps after powering the shop with the Solar Edge inverters, grid-tied inverters. We're still getting 200 to 225 with excursions up to 300 amps for hours into the Powersafe 100. And so this is working extremely well. We kind of stumbled on this AC coupled charging by accident. No one in the industry still believes you can even do this, and we're doing it routinely and without breaking a sweat. Our fans are hardly coming on the inverter. It simply doesn't care if it's putting out or taking in. And so there's our power display. Let's talk about voltage. And here we are displaying the voltage of the cells. And what we're actually displaying here is the average voltage of all the cells. And that ranges from 3 to 4.2. This line is what we set in our controller as our cutoff. This is where we would disable the positive contactor, well, actually both contactors. And this is the low voltage limit, set right now a little above 3 volts, where we would disable those contactors if it got below that. And this gives us our current voltage, the average voltage of all the cells. We actually have a cell view here. And right now I am monitoring set to send me data on 16 modules. So this is a module here. Let's see. This is a module, this is a module, and within that module you see 6 individual bars, and I have them sort of increasing in value as test data, so I can see that on the display. This is our average voltage displayed here of all the cells, and it'll match this blue indicator, which is kind of like your speed on your Tesla Model S display. And these are each module, you can see alternating light and dark bands. That is 16 modules displayed simultaneously, and their voltage levels in the display. If I touch that display with my finger in this area, I get a full screen representation of our cell view. And here you can see the modules numbered 1 to 16, and you can see the individual cells, their voltage level, and our high cell is at 3.875, low cell 3.775, average cell is 2.8 and changing. This is actually not changing data. I'm only experimentally changing the average cell voltage in the UDP packet transmission. And so you can see these paint as the UDP packets come in. And you can even see us miss UDP packets. Like here, this one didn't get caught up in that pass. Here, this one didn't. And so we have about a 10% loss of UDP data packets. This is not a 100% connection. UDP packets are connectionless, and there's no error checking or retransmission. So we're just blasting these packets and receiving them as we get them. This is kind of an interesting data philosophy, but it's very similar to CAN. CAN in a car, you can have 30 devices on one CAN bus, and they're all transmitting more or less at random times. And so there are packet collisions all the time and retransmissions. Well, this is kind of an interesting, if crude, protocol, and it's based on the philosophical concept of, oh well, I missed some data. There'll be some more along here in a little bit, and plenty where that comes from. And so devices on a CAN bus simply transmit often, and the people listening, the other devices that are listening for that data, get it when it gets through. And if you do it enough times a second, enough get through that you can operate. Well, this is ideal for UDP. It's connectionless. It's like CAN, and a lot of packets get stepped on or just get lost. Your AP's doing other things, and both your devices are doing other things. And but you can see in the cell view as it sweeps across sequentially, and we're doing pretty good right now, but here we missed one. And you can see sometimes we're missing packets. Here's one here that it just didn't get updated. Well, it'll catch it on the next sequence. How fast do you have to see cell voltages change? And so this is not only an interesting view in that you get to visually image the voltage of each cell of each module, even on in the case of the Powersafe, a 20 module transmission. And this simply rescales for 20. You can have this monitoring one module, and you'll have big wide bars for 6 cells of one module. And we can do up to about 40 modules on this display. So I've got it set to 16 right now, but it'll be 20 when we see it in operation later. And so this gives us our individual cell view with cell voltage data, our highest cell, our lowest cell, and our average cell in this expanded cell view. We covered power. Well, this is a power log, and as we're charging, we're logging the level here of charging. Now, as you can see, we get down pretty low, and sometimes you're charging and discharging at 3 or 4 kilowatts. I can blow that up with this clicking on this to 2x, and I can toggle back and forth between a true scale of our power and a blown up scale of 2x to see the actual values charging or discharging of our thing. And so in operation during the day, you can actually watch cloud activity as you're charging, and this goes up and down based on your loads, but also simply the amount of sun falling on our solar edge grid tied inverter segments, panel segments, and this actually makes a little map of what's going on. And similarly at night, you can watch it discharging. You can see the refrigerator come on, and loads increase, and you get a little bit of a bump in the demand on the discharge side. We can blow this up again in an expanded view, and this is a little scale of the power involved, and this is an actual a little bit longer view, and of course blown up, and we have to, so I change this back to 1x, you can see the waveform. This is oddly shaped because I'm running up and down the current, but I'm also running up and down the voltage, and they're not necessarily connected. And so you see these odd waveforms appearing. And we'll look at some real data later connected to the actual Powersafe while it's powering the shop and doing that. But this is the power view. We also have here our state of charge of the battery, and it's red below 20% and red above 95%, but this is just a numerical presentation of our state of charge. But I can click on that and I get a state of charge log. Now our thinking on this is evolving, but we're probably going to do this logging at a much slower rate. If we did it every 120 seconds, for example, sampled the state of charge, which doesn't change nearly as fast as our power output, we could have the last 24 hours on this display, showing us our discharge, the state of charge going down at night and coming back up during the day, and we get a big curve here, and that's what we're working to. This is the heart of the melon in operating your system, is to see what level of charge you reach and discharge you reach with your battery system. And if you get the full charge in the afternoons when you have solar, and full discharge overnight, your battery's too small. You want it to charge to about 80% or 90% in here in the afternoon, and discharge to 30 or 40% overnight. That would be ideal, and it gives you some slack for days when you don't have enough sun to really do anything. So you don't want to see it going to 100% during the day and cutting off your solar panels to keep from overcharging the batteries. And you certainly don't want to shut down at night because your state of charge got too low and we had to shut off the battery and your power to prevent damage to the Tesla Model S modules. But this display will let you see the last 24 hours of charge and discharge expressed as state of charge of your battery. And so that's kind of an interesting display. This is still under work, but it's going to be a configuration screen letting you set different things that you can set now with a terminal program over USB in the ESP32 controller, but also some settings for logging and so forth, applying just to the display. And I don't even have this set up to escape from it at the moment, but we can bring this back up, and there's our display. So that this will be where you set your configurations, and you'll be able to do that with this display. And so we're very excited. This is a lot more data and a lot more usefully presented than we ever had on the Andromeda Interfaces EVIC display, which was simply done for the Orion BMS, and it's very basic and it uses CAN. We can connect this display via CAN wire and have much more complete data connection using a CAN board option on the app of the Raspberry Pi, and that's where we started. But we found we could do this wireless UDP broadcast blast of the same data over wireless, and we're addicted to it already. I mean, I can tell you, it's just, I don't want wires, and so this is our display. Where does the future lie with this? Well, we're going to eventually migrate all of our battery controllers to the ESP32. And this is going to be our display. And we can do a lot of things with that. But it opens the door rather broadly. We were going to do smartphone apps to display this data as well. And we can do that with Bluetooth low energy, and that was my first choice. But the smartphones have Wi-Fi capability just as easily. And we can do an app that monitors UDP packets just as easily. And so without making any change to our ESP32 controller software or this display software, we could very easily, not very easily, but we could make a iPhone app, for example, that looked in all respects like this. In effect, to where it would display on your iPhone. Where else does this take us? Well, we've got our Raspberry Pi, obviously, connected to an access point. It is Linux, and so it's entirely feasible for us to also operate a web server on the same device at the same time. As I say, we've got 4 cores and Linux is multitasking now. We could run a web server simultaneously that presents this data in some format with HTML on the web. And if you connected your access point, which undoubtedly you will, to the internet, you would then have the ability to monitor your battery system from anywhere on the planet by connecting to your website on your home access point. If you can expose that to the internet with appropriate domain naming and routing, you could set up a web server that displays your solar power data, basically your battery data, the same data we're presenting here in HTML. And I don't know what that presentation would look like, but you can certainly do a basic presentation, a state of charge, voltage, current power output, and so forth. And there's not really a limit to that. We can take that to listing the voltages of every cell and every module in the battery pack on a website. And so we're very excited about the access possibilities that I saw a couple of years ago, really with the advent of the ESP32 chip with wireless and Bluetooth capabilities. I thought we would be mostly interested in Bluetooth. The Bluetooth implementation, apologies to Neil Colban, but it's just not very good on the ESP32. It would take a lot of work basically for us just to develop libraries to effectively use Bluetooth on the ESP32. It's pretty clumsy. On the other hand, connecting to an AP and sending UDP datagrams are fairly trivial. And so we find ourselves going in a little bit different direction than what we had planned, but wireless connectivity was the objective. And here we see basically in just a few weeks, albeit of intense effort, Colin and I have both been whacking at this together for a couple of weeks, but it really hasn't been that long, and to achieve kind of huge strides in replacing the EVIC display because of the power and flexibility of this Raspberry Pi interface. Now, I'm not going to be able to bring you this at Raspberry Pi prices, but I think we'll be in the EVIC we're selling for about $795. I think we can be at $395 or $495 with this. So cut the price in half, and provide more functionality this way. And you wind up really with a Linux single board computer and 7-inch touchscreen as part of the deal. And so I think this is going to be a tremendous bump in value for the people doing this, but more importantly, better functionality for monitoring Tesla batteries, either in a car or in a solar application. And so we're really excited. I'm really excited about the progress we made with the ESP32. I've got our controller software pretty much fully ported to that, and with some additional features already that are very attractive. And the Powersafe 100 is actually running on that. It will be a few months before we have that as our normal module controller kit controller and this display available. But I wanted to share our excitement and the direction that we're going with this. And I think it's going to set a new level of functionality for a battery control system, basically, for your solar, home solar application. We'll take a look at this connected a little later to an actual Powersafe 100 and show you some real data in the same way. Stay with us.
Hello EVTV viewers. I'm going to do a quick series of videos here about the ESP32 board that we've done, our new work with the Raspberry Pi display, and how that all works with the Tesla battery management boards. I don't have a big stack of battery management stuff like Jack does, so I'm kind of doing a little bit more cut down than he is, but same stuff applies basically. Working on the display a little bit different. I'm going to show you that here in this series. Here we kind of have a quick overview of my setup. You can see I just have a single Model S battery module here, hooked up to the ESP32 boards that we made with a Tesla BMS board on top. Kind of crummy wiring harness here that I made that goes into that. Then we've got this nice case that the Raspberry Pi can go into. There I am in the reflection with my battered up hand after having surgery. So basically you flip this over. You can't fit anything else in these cases that we have here. I think Jack said he found a case where you could. So that's all you can put on here, but they make CAN bus adapters. The boards that go on top of a Raspberry Pi are called hats instead of shields. So here we have a CAN hat. You hook the CAN to these little screw terminals here or to this DB9 port. So I was doing this for a while. You can put a CAN shield on here and our display will use the CAN shield if you've got it. Otherwise you can use UDP through Wi-Fi. I'm kind of partial to Wi-Fi these days just because you don't have to put this on there. Then you can use this nice case and everything's wireless, which is a lot more handy. Reason you might want to use the CAN shield would be for a little bit better reliability. The UDP loses frames sometimes. It's not a big deal because it's sending so rapidly that you'll get one in a few milliseconds anyway, even if you miss one. But with a CAN shield, you could put your display here much farther away, say even 1,000 feet away from your battery packs. You could put this in your house even if things were separated by quite a distance. With a CAN shield or a CAN hat here, you could hook everything up still and you'd get reliable performance. So I'm going to take a break here, put the Raspberry Pi back into its case, and set up things a bit and give a demonstration of kind of how this can work for me, and then I'll go into the PC side. Alright, so here we are. I've got everything hooked up. I've got the ESP32 board with a Tesla BMS board attached to it, all through this wiring mess over to a single BMS or a Tesla BMS here with a ancient set of Thunder Sky batteries as my 12-volt battery. So right now, the only connection this has is to the Tesla battery pack here. As far as wired connections go, it is just using its antenna, which you can't see, but down under there's a little chip antenna on the end of that. And so we got wireless connectivity over UDP frames for our connection to the Raspberry Pi. And here's the Raspberry Pi booted up. You can see that I have been using it. That's kind of debugging info from the display. What we do a lot of times for development, I'll come over here. Here's my laptop. Let's see here. Go to VNC viewer. IP address of that. You can see that that is the same image we have over here, so I don't have to hook a keyboard up to the Raspberry Pi, so I can just remote control it from here. So then with this keyboard I can run the app. You can see that it popped up there. Now it doesn't run super well with my hardware. I don't have all of his nice contactors and current sensor and all that. But you can see I do have the battery pack there, 21.7 volts, 23 degrees Celsius. And down in the corner there, it's showing the average voltage as very, very low because it thinks that I have 20 battery modules installed, but there's only one. So pretty low voltage being reported, and some things are jumping around a bit. Doesn't really happen to Jack. He'll probably show you that this does actually work a lot better when you have real hardware and you're not hodgepodging things together on a table like this. But you can see it's kind of working, and if I come over here, touch that, the cell view blows up. You can see that I only actually have one cell bank, but they're all there. I don't know if we're focusing properly, but those are discrete lines. They actually all look pretty much perfect. You can see that the high cell is 3.615 and the low cell is 3.612. So there's a whole 0.03 of a volt difference between those cells. So the graph looks pretty much like just a big giant bar. We can go out of that. If I had power, you can see that. I'll show that in a minute. Likewise here, I'm at, it doesn't look like it's showing up very well on the screen, but it says 109.5% state of charge, which is a little unrealistic. But that's kind of, you can still see anyway that it is hooking up over UDP. It is getting the data from here, but in my setup it doesn't look very good because I don't have all the requisite hardware that you should have for the solar installation. Close that up. But I will show something here. Let's close our VNC window. The app also technically runs on my laptop, and on my laptop, here I'll kind of explain here. On my laptop, there's, instead of hooking over UDP, which does actually work, I'm not going to show that because it's not really set up for that right now, but technically you can actually run the app on a laptop if you prefer, and that works just the same. On my laptop I have a test program, you can kind of see that here, or it could crash. Oh, you're actually seeing when I start that it's fighting with the fact that it is connecting over UDP to the display, or to the BMS over here. But I also have the stuff that I was talking about running. So let's turn this Tesla BMS off there, and I'll show this here. There we go. So here's kind of a test routine that I can vary things and see how the graphs all look if I actually did have correct data. So you can see over here the graph of voltages. I'm kind of varying the voltages up and down, state of charge, and number of kilowatts, amperage up there. I'm not doing anything with temperature, but if I go into, let's see, the battery pack here, see a blown up view. The cell view looks pretty consistent. You can see I actually am filling out all 20 modules here, and so the average, low, and high can all move. You might notice that the average is sometimes less than low. That's because I'm programmatically varying all these values pretty much randomly, just so I can see what the program does at a variety of values. So these are kind of nonsense values. They don't really match down here, but it's good for testing. So that's what the view looks like on cell view. You wouldn't normally see cell view going quite that rapidly. I'm only basically charging here, so have a consistent green graph. This power log, you can see obviously it only goes for 12 minutes in this case, but it'll give you your last 12 minutes power usage. A nice little graph here. Ordinarily you probably wouldn't see this going quite so abruptly either, but it's matching this. And then state of charge log. Don't really have a lot of stuff that you can see here right now because this is on a 24-hour graph, and I doubt that anybody really wants to watch this for 24 hours straight. So actually I will quickly go over here. Little snippet of source code that's actually normally not open, but you can see the top of it here. Go down here, make. Now if I go over here to the state charge gauge, we have a much faster updating gauge, which now goes for 1 hour of logging instead of the 24.1 that it showed before. So kind of see that it is filling in. This graph goes pretty slow. Obviously, especially on 24-hour, it would go pretty slow, but that will show you your daily usage. You can get a 24 hours in the past log of what your usage was, how your state of charge varied over those 24 hours. Were you gaining energy from the sun? Were you losing it to having too many appliances on? That kind of thing. So all this works right now. In the future, they'll actually be set up here. I'm going to click on it just because I'm on the PC so you can actually see it. This will obviously be fleshed out a little bit later, but right now, currently, you can't get out of it. So that wouldn't be real good if I tried to run it on the tablet like that. So there's kind of my view. You can see debugging info here. The bias settings are showing whether it's bringing its voltage and current and things up, down, or trying to keep it right about even. So There's just debugging info there, output from the program. But this is how I can debug an application that uses hardware I don't actually have. I've got the test data coming through. I do have some hardware here that I can use to kind of test to make sure the connections really happen. But it's kind of a collaborative approach where I test mostly with fake data like this, and then Jack tests with real data on much more hardware. So that's kind of how that all works. Just some more random thoughts on the whole process. You can see that we're using an ESP32 as our wireless sender and hooking up to the Tesla BMS boards. The Tesla BMS boards were originally meant to go on a CAN or on a Arduino DUI or our CAN DUI boards. I made the ESP32 board pretty much pin compatible with the DUI. It doesn't have nearly as many pins. That's kind of one of the crappy parts about the ESP32. It's a really nice fast chip. It's 240 megahertz dual core, so it's many times the speed of a Arduino DUI. Still 32-bit, but it has much more flash and RAM. Built-in wireless with Wi-Fi and Bluetooth. So I would say it's a nice chip. It is a nice chip. It's a fairly inexpensive chip. You could buy ESP32 chips for less money than you can buy the SAM3X that's used on a DUI. So it's very cost effective, very powerful. In the past, it's been kind of crappy in terms of its software support. It seems like sometimes, even in hardware-wise, they didn't always make the best engineering choices. So with the predecessor, I think, was the ESP8266, something like that. They had a lot of issues as well with that when it first came out. These chips really are mostly, they're kind of, when they come out, they're very alpha quality. The software is not there. Half the hardware doesn't have any drivers. Things crash all the time. Performance is bad. Now with the ESP32, we're getting to the point where performance is pretty good. We're still losing some frames on UDP. It's not terrible. We're probably getting at least 80 or 90% of frames through. So when you're sending as rapidly as we are, you just kind of pick up the next one, and if you lose some frames, you lose some frames. It really just kind of evens out in the wash. So the ESP32 has been a really nice processor for us. We're kind of moving to that instead of the DUI. The thing I like the least maybe about the ESP32 is the limited number of pins, where on the DUI we had like 60. On the ESP32 you've got about 10. So we're a little limited there, but I was able to make the Tesla BMS board still work. So we're still pretty much in the running there. The Raspberry Pi, I pretty much don't have anything bad to say about that. It's 1.4 gigahertz, quad core, much more RAM, much more, well, it doesn't actually have storage, but you can put SD cards on it. My Raspberry Pi has a 16 gigabyte SD card, so plenty of space. It needs about 4 or 5 gigabytes to install the normal Raspberry Pi installation, Raspbian. So I've got plenty of space on that. The Raspberry Pi is a pretty incredible thing, even with hardware 3D acceleration and video acceleration. So you can go on the internet with it, use it as a normal PC, watch movies, surf the internet. It's got HDMI, so if you want to hook it up to a bigger monitor, you can. I don't know if it supports 4K. I've got a 4K monitor over here, not in the shot, but I haven't tried that yet. But the Raspberry Pi is really, it's a very good price for what it is, pretty cheap. Even these displays that are on there, they're not tremendously expensive. I'd say all of it together is cheaper than the previous displays we were trying to use for things. And also much faster, higher resolution. The 7-inch display that I showed is 800 by 480. That's not a particularly high resolution, but it does the job. It's enough for this display that we're doing to have pretty high resolution. The display There's enough horsepower there. The display updates 10 times a second. We don't have trouble with that, whereas our previous displays that we were using had trouble getting about 2 or 3 frames per second. So the Raspberry Pi is just so versatile, and with it also having Wi-Fi built in, it's just perfect to wirelessly connect things. I could bring the display into the other room and not have to have any wires. You could put your Tesla BMS stuff out in your garage and have your Raspberry Pi in the kitchen and still have it work over wireless. Now, the other nice thing on Raspberry Pi that I kind of liked is that it runs Linux. I was talking previously about Raspbian. It's a Debian installation for Raspberry Pi. So the whole thing's Linux. That's why I was able to easily run the same program on the Raspberry Pi as I do on my laptop. It's the exact same source code. I compile it the exact same way, use the exact same libraries. It makes it very easy to do development on the Raspberry Pi and easy to get help because it is a pretty much vanilla standard Linux installation just on a really small board. So that was nice. I'm using Socket CAN. If you know anything about Linux, that's, basically UDP is using Linux sockets. And if I put the CAN hat on there that I showed, you use Socket CAN, which just runs CAN over sockets. So the entire application is able to just use Unix sockets either way. And things can connect very easily. It's very easy to debug because if you are having any troubles or questions, you can run standard Unix utilities. I could run Wireshark directly on the Raspberry Pi and do network analysis that way to find out if I'm actually getting a connection. Am I getting the UDP frames to the device? So very handy, very easy for development that way. It's the same Unix or Linux system that I'm used to, and that makes it pretty simple. So I think that's it for now. Hopefully that's interesting to people and kind of gives you a little insight into the background workings of how this all comes together.
All right, let's take a look at our Raspberry Pi display unit with our software. We're still making great progress with this. This is actually connected to the Powersafe 100. It's about 12:30 on a Tuesday afternoon here. And we're kind of cloudy, overcast. It comes and goes, so the sun's peeking in and out. Here's our graph of our power, and you can see it builds up to close to 8 kilowatts, but it's all over the place as we go along here, as the irradiance of the sun varies, and of course our loads vary here in the shop. But this is what we're primarily seeing is a change in output of our Solar Edge grid-tied inverters, which are powering the shop and have extra left over to charge our batteries. And indeed, you can see we're charging right now at 3.26 kilowatts of power going in. Here's 74 amperes of current at 43.5 volts going into the battery. And we're at 67.5%. Colin has already modified our state of charge log to do my 24-hour thing. And so you can see our state of charge climbing since I put the new software on and fired it up. And this is about 24.1 hours from edge to edge, and so this will fill in over the next day, but I'll be able to see the state of charge climb this afternoon when we're charging here in about 25 minutes. We'll be at the peak noon, solar noon at 1 o'clock daylight savings time, and then that charge will taper going into the evening, but then overnight we'll go back down, and by tomorrow I should have this whole thing filled out and be able to see exactly what's going on with our daily cycle of state of charge. And so that's very cool. I like that a lot. Here is our cell levels we talked about. Now, of course, they were very regular with the test data simply climbing in the other view I showed you with the test setup at home. This is actual cell data, and it's being painted more or less continuously. We're getting very good reception here at the shop of our UDP packets. We're not dropping very many, as you can kind of see. I just get a lot better signal strength here at the shop for some reason. 58, 60 minus dBm compared to 80s, 70s, and 80s at home. So we're getting a lot of our UDP packets through, but the cells vary as those packets are picked up and paint different values. But you can see we're not exactly at the same level on all these cells. Boy, this module's very even, but the rest of them are pretty ragged. This one's very nice. But we're talking hundreds of a volt. This really gives you a very good view. We're at an average cell of 3.625. Our lowest cell is 3.551. So that's a little over 7 hundredths of a volt from the low cell to the average. The high is at 3.689. So we're at like 9 hundredths from the lowest cell in 120 cells to the highest. I had a call with somebody today who was talking about the differences in his modules across his batteries. He kind of had a kludgy connection while he was charging. And again, we got into I squared R loss theory, but we've given you a tube here to kind of see, a meter to see things probably in a little bit more depth than they warrant. Here's our needle showing a little over 3.6 volts. This is actually our average voltage here, 3.625, and that's repeated here. So we've got a great view of 20 modules with 6 cells in each module of exactly what their voltages plot out from 0 to 4.2 volts full scale here. And this will gradually creep up the screen as we go up in state of charge. So I'm very happy with that. It's kind of a cool day here. We're not doing a lot of power. There a little while ago we were doing 330 amps, about 14 kilowatts, and the inverter was beeping an alarm at me about to shut down, but I guess some clouds intervened and we escaped the ignominious fate. But as you can see, we're climbing in state of charge. We're charging. And again, I can't quite get over it. It's like charging for hours, AC coupled from grid-tied inverters into our thing. I don't even have our input to the Powersafe connected to any AC input. In fact, the building isn't connected to any AC input. We've got the grid shut off outside, and we're powering the entire shop during the day. Refrigerators and coolers and the whole thing, and still generating enough solar power to charge our Powersafe using our 25 kilowatt production array. I don't even have the 13.5 kilowatt test array hooked up to anything today, and so this is going pretty well as far as that goes. And so we're coming up on it's 12:44, And as you can see, there's a little bit of sun peeping out from the clouds. And so our current and consequently our power is creeping up. And here's our state of charge growing slowly as well. So we have a much slower log here. Left to right will be 24 hours of logging, where left to right here is 6 or 7 minutes. Because we're actually kind of for test purposes logging this every second. I would say, and that's going to be a configurable item that you can set to what you want, but I would really look at 10 seconds or 20 seconds to be a good time to do it. It depends on what definition you want to see, but at 1 second you get every little change logged here. But that's largely for test purposes. In normal operation, I would have that set to 10 seconds probably, or even 20. Now you can't see it here, but this software also prints out to the SD card in the Raspberry Pi a text file log, taking all the measurements every second and time stamping them into a text file with the date, the time to the second, and then it lists our voltage, our current, our power, our amp hours used, and the temperature in comma separated format. That will allow you to have a very detailed graphs and charts and so forth that you can import that comma separated file into Microsoft Excel or whatever your favorite spreadsheet program is, and graph any of that data to your heart's content. The ESP32 controller does not have the EEPROM on it that our CAN DUI does, and it's there is some NVRAM things you can do. I can hear the inverter alarm going off because we're charging at 279 amps, 290 amps here, 13.5 kilowatts as the sun comes out, and that's well, there was a sudden change there. I don't know what happened here. We suddenly lost all our charging. We're still making power, but our solar input has kicked out, and I don't really have a way to do that. We're going to have to investigate that a little bit. We were just at the point of overloading our inverter, and now it's kicked out. We're making power. About 3.3 kilowatts is right for our power output if we had no grid power working. So that's kind of an interesting turn of events here, right while I'm filming this data and observing the system. We'll have to take a closer look and see what happened there. So that was a little bit interesting. It turns out when it got up to a very high power level here, the inverter did something, some sort of a hiccup. We never lost power at all. There wasn't a flicker of the lights. but all of our solar edges went off. And here we are outputting power. And then, without any intervention on my part, 5 minutes later, and you can see that his time minutes in the past mark is pretty accurate. A little over 5 minutes later, they all came back on. And so we're back to charging, and at pretty high rates, 12 kilowatts and so forth. But if you get up to 14, 15 kilowatts, the inverter did something that threw off our solar edges, and they simply went away. Let's see if it does it again. I got some sudden sunshine here, and we're up at 10 or 11, 248 amps. Let's see what transpires, see if we can get it to trip again. Big trucks going. This is a fun neighborhood. Trying to film in. So, but you can see here we were charging at a very high level, and then suddenly cratered, and we're putting out about 3.5 kilowatts. So that's interesting. That's about what we were using, about 3.8. And then 5 minutes timeout on the solar edges, and they came back up. And here we hit a peak. And so we're charging along at a pretty good rate now at a 69% stated charge. And powering along pretty well. So I guess the takeaway is already our Raspberry Pi display system is very useful for observing our basically the operation of our solar system. We're really monitoring the battery, but the battery is the heart of it in this case, and kind of everything flows from that, including our inverter output or our charging input, and that varies during the day. If we go to enough overcast, we won't be getting any power from the solar edges, even though they may be producing a little bit, and we'll be having to augment with the 12 kilowatt inverter in the battery. And that crossover from charging to discharging is entirely automatic. There's not even any software involved in it. In the Engineer, it's simply switching. It thinks it's making this power. It doesn't know that it's coming in backwards. They just didn't expect to have that, so don't have the instrumentation to read in reverse. Otherwise, they might stop it. But the way it's working right now is perfectly. The anomaly we just observed was that with very high rates of charging, that at some point it will kick off, and I don't know how it did this. The solar edges lost confidence in the waveform from the Engineer and kicked out, and they all went down simultaneously, and then they all started coming back up together 5 minutes later, which is their normal timeout period when you first turn them on. And so we're back charging happy as a clam now. And we never lost power. This transition, it wasn't a flicker of the lights. It was seamless. But it must have gone off frequency from the strain of several minutes up at high power levels. And that was enough to kick off the solar edge grid-tied inverters. So I've never seen this before. But on the other hand, I haven't had anything to see it with, really. The EVIC display is nice, but it's pretty basic. Suddenly I can see things over time. I can see cells at a very detailed level of their voltage. Well, they've all seemed to have smoothed out. There's some data. And so you can see them moving around a little bit, particularly as we get up. I guess they're more excitable up here at 10 kilowatts than when we go down in power. Once in a while, if we don't get UDP packets often enough, we'll simply reset everything. That way, if we lose UDP connectivity, we don't just have a frozen display and still think we're alive. It actually does blank, but it picks right back up on receipt of UDP. So yeah, it's 1 o'clock right at our solar noon here. And we're cranking out, there's 13.67 kilowatts. And that's above the 3.8, I think, that we were using when they were off. So we're putting out about 16, 17 kilowatts on the solar edges, which I would say is disappointing in August. It's supposed to be a 24 kilowatt array. At high noon, as they would say, that we're getting 17 or 18, but that is the real world with solar, and like everything else, it's a little bit over advertised. It's still a pretty good amount of power. 17 kilowatts is pretty nice. And so again, here's our graph. We can actually see the clouds coming over. This is not an equipment problem here. There's a little bit of variation in our loads here in the shop when the refrigerator comes on, but nothing you would really notice at the 1x scale. This is all changes in the radiance of our solar panels, and you can kind of watch it in real time and with this graph see that action. And as I was saying, the crossover from charging to discharging is all graphed, but it's the equipment doesn't it's not really cognizant of it. It just happens automatically. And so sometimes of the day we're putting in a lot into our batteries above our needs. And this would all normally be going out to the grid at 2.4 cents a minute. And then at night we'd be using from the grid at 12 cents a minute. Well, that's not really what I want to do. And so that's what this trade is about. We'll take the sunshine and store it during the day and use it at night and let them keep all theirs. And there you have it. So that's some real data on the latest version of our software. I just got an update from Colin with this handy dandy state of charge 24-hour rolling graph that I'm quite excited about. I think this is really the heart of your system, is how high up you get in the afternoon and how low you get in the early morning hours. And that goes to system sizing. And as any of our solar veterans know, you kind of add to that over time to tune it into what you want. I was talking to a guy from Kentucky earlier today, and he just keeps adding batteries and so forth. Again, our controller can handle up to 62. Now, I can only display about 40 and this display at that just gets, the bars are so narrow it gets to be faint and ghostly looking, um, and so we've limited it to about 40 modules on here. But that's the state of the display unit, and I gotta have to tell you that I'm delighted with it. Stay with us.
I have something I want to talk about. I don't really have a teleprompter like Trump or the newscasters. I hate to read this to you, but I'm more of a writer than I am a titty blonde on TV, and this gets a little bit geeky. In fact, this whole episode of EVTV, you're going to find a little bit geeked out. I've made no secret that I don't really like 48 volt DC batteries for solar storage, and advocate using electric vehicle batteries at their native voltage, which is for almost everything on the road, nominally 345 volts. You'll charge them to 400 or 402 volts, and you're pretty much shot at 300 volts. But the nominal voltage of the 96 cell packs that have become almost an industry standard is 345 volts. But I'm coming around on the topic. We have several full packs, 3 of them, floating around here in the shop. One of them I've been using already is showing signs of having one defective cell in one module. And what do you do with that? We haven't even opened the battery. And so, in addition to being unwieldy, they're 1,380 pounds. If you do have a cell go bad, you pretty much have to take the pack apart and salvage the modules, which is no great sin. The modules go for $1,400 or $1,500 a module now. The Tesla Model S battery modules have become very popular, and increasingly so, and particularly for solar storage, but people are also using them in cars now. So I like the full packs because you can just buy them. I've got a device you can just plug in, turn it on, and you've got a battery. If it goes bad, you get another one and plug that one in. But they are big, they're unwieldy. And the Tesla modules, you can start out with 2 of them and kind of collect them, trade them with your friends. They're 56 pounds, 2 feet long, 1 foot wide, and 3 inches thick. Anybody can pick them up, move them around. Anybody can build a rack to store them. And so that's been the main area of popularity. They're just much easier to deal with physically. And so the 48 volt systems are popular. The other issue is the solar equipment manufacturers, who started out at 12 and 24 and so forth, are up to about 48 volts as the power demands rise. But all this was done to cater to a world of very large, very heavy lead acid batteries that take a lot of maintenance. You have to be able to get to them, and you have to replace them fairly often. And so 48 volts has emerged as kind of the standard. I have to say that I have developed some affection for the 12 kilowatt inverter that Engineer made for us with voltages specific to the Tesla Model S module. We're entirely sold out of these at the moment. I'm waiting for some new ones. And I'm pleased to mention, and I probably shouldn't, but it's been put off a month as a Chinese had to go on parental leave to go take care of an aging parent. But we have a new version coming that will be 15 kilowatts peaking to 45, and they've agreed to some other minor engineering changes. More on that later, but it should be interesting. But I've always had a problem with the 48 volt DC systems conceptually. I see all over YouTube now little videos about housewives and guys wanting to tell you the truth about solar. And these are kind of tiny house nation guys out in the Montana wilderness talking about how you have to make sacrifices to live off-grid with solar because of the long winters, and you can't use the vacuum when you're using the dryer, and you have to wait to take a shower because the well pump runs on electricity, and you have to run the air conditioner up at 88 degrees because you don't want to use too much electricity because you don't have very much. Well, I don't want to wait to use the dryer or the vacuum cleaner, and I like the house to be 70 or 71 in the heat of summer and 74 or 75 in the cold of winter, and that takes power. It's not a great deal of power as we're accustomed to discussing it with electric vehicles, but 3,000 watts doesn't get it either, and it isn't a 10 kilowatt hour battery. That's not going to quite cut it either. I deeply believe in improving life on Earth through the use of the development of technology, but I don't want to suffer for the planet. That's not the mission here. It's to live a normal life and even a energy-rich life using the magic rocks of photovoltaic panels and lithium batteries to do it, and I'm convinced more so now than ever before that it's actually quite doable. But my vision of solar is big solar, enough solar and enough storage to run a full-size home in comfort year-round without really depending on the utility grid at all. And that takes some doing, and it comes at some expense. Now, understand, whatever I'm doing does not make economic sense for consumers when I'm doing it. It does 5 or 6 or 8 years later, but at the time I'm playing with it, it's all too expensive, too clunky, and too cobbled together. We've been doing quite a bit of testing on the Powersafe 100, and I have to tell you, as you learned earlier today, things happen. You can't simply type yourself smart using a keyboard on the internet. At some point, you have to hook stuff up and run it and observe it carefully. And don't assume that things are simply anomalous. They happen for a reason, and surprising things happen, and sometimes for surprising reasons. And that's what testing is about, and it's how you learn things. We powered the shop for several days, draining it down to, about nothing, a very low value, and then we recharged it from the grid using the built-in charger in the 12 kilowatt inverter. I'm going to share some lessons learned that may seem a little bit boring to you. And they're going to seem boring because you already know it and you know all about this. The part I want to impress on you is just to open the possibility that you know it wrong. As a fortuitous accident, Engineer didn't do a really good job of setting the voltage limits I asked for. I wanted to discharge the battery to 36 volts. And I thought 3 volts per cell would indeed be somewhat generous. As it turns out, not so very much. We recently published a discharge curve on the helicopter battery, And even I was surprised to see that going from 19 volts, 19 and a half volts down to 18 volts, there was 6 or 7 amp hours difference. This is the part of the curve where it goes very steeply down. The other issue that we're learning is that Tesla top balances these cells, and they do so kind of automatically. We have to trigger that, and we've retained that functionality in the Tesla BMS boards, and exercise that. It's a little goofy when you have multiple modules in parallel. You understand when they do it in the car, they're all in series. But we do it by keeping them all at the top. There are still differences in capacity of the cells, and as we've described for years here at UDP, when you do that, you present all of the difference at the bottom. And so in discharging the pack, we find that some of the cells are alarmingly low compared to the other ones simply because they're lesser in capacity. So you don't want to push that lower side of the discharge curve. As it turned out, fortuitously, this engineer did not follow my instructions, setting a low voltage cutoff at 36 volts. In our measurement, it cuts off at 38.65 volts, just under the 39, which happens to be where the big knee is in the discharge curve anyway. So with blind luck and malfeasance and incompetence, they just happened to err to exactly the point that I now would want to have a low voltage cutoff. So that's worked out pretty well. In the Powersafe 100, cell 3 and module 1, when we're down around that level, went down to 2.65 volts. And cell 3 again in module 5 was well under 3 volts, when all the rest of the cells were up around 3.22. So discharging below that 38.65 volt level, at which point the inverter cuts off, and if you're plugged into AC, it would start charging the batteries automatically. That would actually be very fortuitous. The Model S modules purport to be 220 amp hours. With 10 sets in parallel, we should then have 2200 amp hours. We're measuring more like 1800 to 39 volts, and that's about 78 kilowatt hours, not precisely 100. Now, we don't charge them all the way up to the equivalent of 402 volts. I have to point out that Tesla advocates the same thing, not fully charging the batteries, and they're fairly emphatic about it. Minimize supercharging and charge to 80% if you want to maintain long battery life. 78 kilowatt hours is still quite a lot. But when we started charging using the AC input, and I do have a little trimmer pot on the inverter that you can actually modulate that, but who wants to charge at a lower rate? And so we charged at 110 amps. That's about 4,000 watts at 39 volts, and maybe 5,000 watts by the time we get up close to 50 volts. But in any event, 78 kilowatt hours at 5 kilowatts is 15 and a half hours to charge on AC at 110 amps. Tesla superchargers recently have gone to 120 kilowatts, and at 400 volts, that is indeed 300 amperes, but you only need to do that about 40 minutes to completely charge a completely empty battery. So we got a little difference between 15 and a half hours at 110 amps and 40 minutes at 300 amps. And this brings us to the real issue, which is heat. Now, when I say this 110 amps, on the Tesla car at 300 amperes, that's into all the modules because they're wired in series. When I'm putting 10 parallel sets of 2, if I did that at 300 amps, it would be 30 amps per battery. So we're not overstressing the batteries, and we're not really overheating the batteries. But we monitor temperature at the terminals of the batteries. We were charging the pack, and I got doing something else, and went over and was surprised to learn that the whole system had shut down. And further investigation showed that it wasn't the inverter that had shut it down. We had disconnected the battery pack on a temperature alarm, which is exactly what it's supposed to do, but I had it at a fairly high level, like 55 C. I cleared the alarms and reset the system, and we resumed charging, and it worked fine for about 4 hours. But I did notice we were up over 50 C on modules 17 and 20, which are the top batteries. The ones closest to the inverter. I opened the door and hit the terminals and packs with my handy Fluke Model 516 infrared thermometer. This isn't a DeWalt or something cheapo. This is a Fluke Model 516, and it's reasonably accurate infrared thermometer. And I was very surprised to see the temperatures were up around 78 degrees centigrade on the top 2 modules at the terminals. This is way beyond what I want to see, and more than a tad bit alarming. Tesla on the Model 3 faults out at 48 degrees centigrade. Worse, it wasn't what we were reading from the BMS boards. We're indicating 50 C, and it's really 78 C. So what's going on? In truth, the code we developed reads the temperatures a value of resistance from the thermistors that are used as temperature sensors. And we have to do the calculation of the temperature from that. And we kind of carefully calibrated that algorithm, but between freezing, 0 degrees centigrade, and I would say about 35 or 40 degrees. And I'm pleased to report it's quite accurate in that range. But that curve apparently takes a pretty big bend as it goes up. We're probably good to 45, but from there on up, we diverge from reality rather markedly. And we're going to have to revisit that polynomial calculation of temperature from resistance on those thermistors. There is an algorithm for that available, but you have to make a couple of assumptions, and we're going to have to revisit that whole issue. But my issue with 48 volt systems has come to roost. It was not only a fear, it was not only not groundless, but pretty much my sense of it, without doing a lot of calc work, was that it wouldn't work. It works, but my sense was exactly right. I'm going to hear, and I've already heard, a lot of very sage, condescending, and even patronizing advice on cooling strategies. I don't really need it. In the first place, there's not enough cooling in the world. The ambient temperature in the cabinet does rise, but it's not the problem at all. Understand that we're having much higher temperatures at the two terminals closest to the battery than we are at the bottom. And that tells me one thing, it's current related. You see, the inverter is putting out the 110 amps. As I said, that works out to 11 amps per battery set of two modules in series. At the top of the silver-coated copper bar, we're carrying the 110 amps. But 11 of those amps go into modules 17 and 20. So on the next battery set, we're carrying about 99.5 amps. And that set gets 11 amps. And so we're at 88 amps below that, and 77 and 66 and 55 and 44 and 33 and 22. And at the bottom of the bar, we're only carrying 11 amps of current into the modules 1 and 2. And that's how I know where the heat loss, where the heat problem is. And the issue is I-squared losses. I-squared R is actually pronounced and written I-squared R losses. One of the vagaries of the internet and the keyboard is making the squared symbol is inconvenient. So everyone doesn't type I-squared R, they type I2R, and I'm even hearing it pronounced I2R now. That's not precisely correct. And even then, I-squared R is shorthand for an equation. It's part of an equation derived from Ohm's law. George Ohm published a treatise in Germany in 1827 on the relationship between voltage and current. The higher the voltage, the greater the current flow. Now understand, he didn't have voltmeters and ammeters because those kind of depend on Ohm's law, which wasn't invented yet. He's the guy. But they did have ways of roughly estimating voltage and deducing current. And so he noticed a relationship that if you increase the voltage, you increase the current. Of course, he had to make about 10 Brazilian measurements to define this. Again, you can't type yourself smart. You have to do the testing. And he noticed some errors in his calculations. And that was because he would use different lengths of wire to connect the batteries, which are kind of a known voltage, and to measure the current. And so different lengths of wire have a different amount of resistance, was his theory. And therein lies the tale. The discovery in the documentation, rather circular relationship between current, voltage, and resistance. And so his original thing was the current, which he abbreviates capital I, equals voltage, abbreviated capital V, divided by the resistance, capital R. That enabled a number of further calculations. Of course, power in watts was defined by James Watt. He also gave us horsepower. But if you multiply the voltage times the current, voltage in volts, and the current in amps, you'll get power in watts. So 1 volt times 10 amps would be 10 watts, or 10 volts at 1 amp would also be 10 watts. And that relationship is kind of important. But we found mathematically that you could then derive that using Ohm's law simply from current resistance. And the power in watts is equal mathematically to the current squared divided by the resistance. And this observation holds true in all measured instances, just as Ohm's law was, and so we refer to it as a law more than a theory. What does it mean to us? It means that power or power loss as heat is a function of current, not voltage. You can have 17,000 volts across the circuit or 17 volts, and the power losses would be the same if the current was the same. Now, that would require the resistance to be different, obviously, but voltage has no power loss component by itself. Only the resulting current does, and this is literally caused by free electrons encountering other electrons and elements in a conductor. We think of electricity as going the speed of light. It actually crawls through the conductor at about 2 inches a minute. And the conductor, no matter how good it is, has some resistance to current flow. So at 345 volts, for the same power output, 10 kilowatts, say, you would have 28 amps. And to do 10 kilowatts in 48 volt systems is 220 something amps. And it's the current that causes heat and the loss of power as heat in the circuit for any given resistance. Let's do a problem here. We were charging at 110 amps at 45 volts. Our conductors are silver-coated copper bars. We invested $245 in those 2 copper bars. They're electrically a very high-grade conducting copper, and they're coated with silver, which is a better conductor than copper is. And while it tarnishes, it doesn't to the degree copper does. So they're very low resistance. Then we have bolted connections to the terminals, and we use the wedge lock washers, and we tighten those pretty nice, and we kind of brighten them up with some abrasive before we assemble them. And so these are very good connections, very large bars. These are not little cables or even 2-aught or 4-aught cables. They're solid copper bars and our braided battery straps. We don't really have any cables in the Powersafe 100 except to take those bars out to a Rebling connector for external connection to DC coupled solar that isn't going to be very high current anyway. Let's say the resistance of those bars and connections is a pretty low value of resistance. Let's say 10 milliohms or 0.010 ohms. This is 10 thousandths of 1 ohm. Well, if we square our 110 amps, we get a factor of 12,100. And when we multiply this by our very tiny resistance of 10 milliohms, we get 121 watts. Now that doesn't sound like very much in the scale of the power we're discussing, but it refers to losses of power as heat in the conductors, not in the cabinet, not because the inverter got hot, not because the air got hot, but in the conductors themselves. And I can actually measure a difference in temperature from the top bar to the bottom because they're carrying different amounts of current. That's why I know where the problem is. 120 watts. We all have some experience with a 100-watt light bulb. Have you ever reached in and tried to unscrew one while it was burning? It will fry your fingers. You will not remove that bulb with your bare hand. You'll put it right back. It gets hotter than $700. It might surprise you that incandescent bulbs are not very efficient. A incandescent bulb typically gives off 16 lumens of light per watt. That's about 1,600 lumens for a 100-watt light bulb. And that actually converts about 2.2% of that power into light, leaving 97.8% of it lost as heat, and of the 100 watts. Ergo, my view of the madness of, let's say you have 1,500-watt bulbs in your house, you've got 1,450 watts of heater going while you're trying to air condition the house to cool it down. And so it's quite a bit of heat, and heat is cumulative. If you don't get rid of it, it simply builds up. I've actually got those bars wrapped in silicone rubber, which is kind of a good heat insulator, but that's because I need a good electrical insulator. If you get across those two bars with something metal, a chair or something, I don't know what 10 sets of Tesla batteries would do, but I suspect it would simply turn the whole Powersafe 100 into an enormous fireball, and they would find EVTV as a smoking crater, and with no remains from us to be prayed over. So you can't really escape I²R losses, and it's a very cruel reality of electronic design choices, and 48 volts DC as a solar energy storage medium is just a famously poor choice, and it's because of I²R losses. Let's reverse the whole problem and produce 10 kilowatts of power from the system. We're growing over 200 amps. And now we're talking about 400 watts of power loss as heat in the bars, in my contactors, in my bars. And I can actually take that thermal gun and paint it down the row of battery terminals, and it works out perfectly mathematically. Let's take 10 kilowatts on our 350 volt system. That's 28.57 amps. We're down to using 12.3 house wiring, and using our 0.010 milliohms, we're talking about a 2-watt power loss. You'd need 5 of those to make a Christmas tree light bulb. So the much higher voltage is a huge ally in having much lower currents by an order of magnitude And that order of magnitude is squared in calculating heat losses. And this is why I don't really advocate 48-volt systems for solar energy storage. Now, I've said all that. Let's review the history of EVTV. I've been right about a lot of things that just don't matter. People can afford to pick up 2 of the Tesla Model S modules, and they're able physically to pick them up and carry them across the room. They can conceptually deal with the idea of building a rack for them. And if it works with 2, it'll work just as good with 4, won't it? And it'll work even better with 6. And so you have a modular approach when you use modules, and your equipment costs are a lot lower. It's hard to find inverters that operate in the 300 to 400 volt range. I can get you some, but as I mentioned, and we haven't really followed up, I have done some testing with our spark-proof, explosion-proof 20 kilowatt inverter. But again, the damn thing's 500 and something pounds. And by the time we ship it from China, if something happens to it, who pays for it? The Chinese, me, or you? I mean, it's just kind of impossible. The 12 kilowatt inverter's $3,000. You know, we'll work it out. I actually bought a set of replacement boards. If you have a board blowout in your thing, I can just send you a board from here. And this engineer guys are very good about working with people that do have problems. So far, our experience with the inverter has been flawless. But anyway, it's not $20,000 and it's not 500 pounds. It is 175 pounds, but it's everybody's got a lot less invested on the table at $3,000 than they do at $20,000. And so it's just easier to deal with. So I admit the solar equipment is more easy to deal with at the 48 volt level. And the batteries are easier to deal with at a 48 volt level. And the equipment's a little easier to deal with at the 48 volt level. But the I-squared losses are a killer. And blowing fans or blowing liquid through the batteries, it's not the batteries that are heating up. It's the conductors to the batteries and the terminals. And they're heating up a lot. They're getting hot. And they can, at some temperature, set off those batteries. And so I have some concerns over current levels. Now, if you can do a 5 or 6 kilowatt house, that's fine. But if you need 20,000 watts, and we don't have one, as I say, we'll get this 12 kilowatt. Our next shipment will be at 15. But as we go up in power, the current levels required at 48 volts just become absurd. Now, it is possible to wire your same modules in series, 16 of them, for 345 volts, but again, getting an inverter is somewhat expensive, and so you can't really put a toe in on this. You kind of have to go all in to do a 340 volt system, buy a whole battery, buy an expensive, relatively expensive inverter, and so I understand why it's 48 volt world, but I want you to be aware of this. I'm getting calls every day. My batteries are charging unevenly. I'm getting advice from solar professionals. Oh, you got to hook it up at the corners and so forth. It's absurd. It's not the batteries. and they're all kind of held at the same voltage. It's losses in the conductors. You're not using big enough cables. And it's an issue when you get above 5 kilowatts at a 48 volt system. Well, that's 100 amps right there. And so your I squared R losses as heat become an issue that you have to deal with. And it's not that easy an issue. You don't just blow air over it. It's an issue. So that's the take on voltages and so forth. But we are going to pursue the 48 volt end of it. I made some very nice full pack controllers, and most of the world doesn't care. They are the way to go, but nobody wants to deal with the weight and the expense of full Tesla packs and the weight and expense of the inverters. Most of the DIY guys want to start small and build it up incrementally. I get it. We'll learn to play with you and try to enable you as best we can. But I want to establish a foundation for what one of the central problems you're going to be designing around over and over and over again has to do with high current levels and heat. That's it for this episode of EVTV. It's probably longer and geekier than you really want to follow, but that's who I am and who we are and what we do. And we do have cats, but they don't really star in the videos. An occasional cameo appearance, but we don't run things through blenders. We're probably not going viral on YouTube. In fact, we may be kicked off at any time for being a bunch of conservatives, which is absurd. I've actually always been a liberal, but it's the nature of the times we live in. So stay with us. There'll be more EVTV, and we're actually quite enthusiastic about our developments in solar energy storage. The charging from AC-coupled, grid-tied inverter systems is going famously. I have a brand new shipment of In-Phase IQ7X microinverters in, and we're going to be testing with them to see if we get as good a result as we get with the Solar Edge. A little birdie has been telling me about the In-Phase IQ8, which is going to basically get out there and validate everything I've been saying from In-Phase. But it's they're hoping for the first half of 2019. I've been following this company for several years. That means 2021, probably, but certainly 2020. But it is interesting the direction they're going, and we're going to be covering that in some depth. Stay with us. There'll be more EVTV, albeit irregularly when you're elderly and COPD suffering host as he eats KFC and smokes Camel cigarettes through a world of wholesome health activity all around him can do.